us about Axion Strings.
Okay, so thanks very much. I'm talking about a work in collaboration with Ed Hardy from European University and Giovanni Villadoro from STP Trieste. And the talk is based on a paper which came out in June and also on ongoing work. And what the title of the talk actually means is the calculation of the QCD Axion density in the scenario where it's determined by the decay of topological defects of the Axion field, which are cosmic strings and manifolds. So I will start off with a quick introduction of just the Axion matter. I guess part of the audience is familiar with this topic, but I'll try to be pedagogical. And then I will turn to the main topic of our work, which is the dynamics of Axion strings. In particular, I will try to convince you that understanding the dynamics of Axion strings is very important for Axion phenomenology. And also, I will try to say which are the really important quantities we want to determine in order to get a sharp prediction for the axiomatic density. And in the end, I will draw some conclusions and outlook. So let's start with just the axiomatic matter. So, as you know, the standard model is an effective theory, so you should include all dimensional 4 and less operators that are allowed by the gauge symmetries. In particular, you should include the glue term of the kind θ0 G dual, where θ0 is a dimensionless parameter and the G is a glue field strength. So although this term is a total derivative, so it has no effects in perturbation theory, when it's taken in combination with the overall phase of a Workman's matrix, it has physical effects. In particular, it leads to neutron EDNs, which are bounded to be absolutely tiny by amazing experiments. As a consequence, the physical parameter theta, that is θ0 plus the argument of the determinant of Workman's matrix, is bounded to be less than 10 to the minus 10. And then this is a fine-tuning problem because both these terms, θ0 and the argument of the determinant of the Workman's matrix, are order 1, due to the order 1 speed violation in the CM sector. And so this involves a fine-tuning of at least one part in 10 to the 10. And this is the so-called famous strong field problem of the standard model. So lately there has been some discussion about solving this problem using anthropics, as you would do for a cosmological constant problem. But the first approximation, it turns out that this problem cannot be solved using anthropics. This is because theta of the order of 10 to the minus 2 is still fine for large distant physics, and so you cannot really argue that theta should be so small in order to allow for life. So this problem actually begs for a dynamical explanation, and the best explanation we have for now is the QCD Axion. So the idea is to introduce to the theory a global E1 symmetry that's called the Peche-Quinn symmetry, that is spontaneously broken at a high scale FA, which is called the Axion decay constant, and is bound to be bigger than 10 to the AGV by astrophysical constraints. So the dynamical Boston boson that arises from the symmetry is called Axion, and it enjoys shift symmetry. So we also require the symmetry to be anomalous under QCD, so that by Toft anomaly magic conditions, the Lagrangian will contain a term of the kind A over FA, G dual, that is the only term that breaks explicitly the shift symmetry. As a consequence, the Axion is Axion Boston boson and has a mass. So at lower energies, QCD confines, and the Axion gets a potential that is completely determined by non-perturbative QCD dynamics. Particularly, you can show that this potential is always minimized at the discrete personality value A equals 0, as shown in general by a theorem by Buff and before. And as a consequence, the Axion solves the strong field problem dynamically and automatically because the effective theta term around the minimum is the value of A over FA, which is automatically set to 0. So, as a consequence, the Axion automatically solves the strong field problem just because of this theorem. So the Axion potential can be computed completely by molecular dynamics, and you can show that it's periodic of 0 to pi FA, And the axion mass is the second derivative of potential minimum is given by lambda QCD squared over Fa, where lambda QCD is a parameter of order 100 MeV. So the mass is completely determined as a function of its decay constant, and as soon as you fix the decay constant, you also fix the axion mass. So this is in contrast to the so-called axion-like particles, where instead this relation is generic. So soon after the QCD axion was introduced, it was realized that it was very easily solve another problem of the standard model, which means to provide a dark matter candidate. And the way the QCD axion solves the dark matter problem is very elegant and almost automatic. In the sense that as soon as we introduce the QCD axion in the theory, there will be always an irreducible contribution of the dark matter, which will be made by QCD axions. This contribution will not, in general, make up the full dark matter density, but at least a component of it will be made by QCD axions. So the way QCD axions are produced in the early universe is the so-called misalignment mechanism, which is based on the fact that initially in the early universe, the axion was initially in general misaligned compared to the severe perturbing value A equals 0. So in the early universe, the axion field solves an equation of this kind, where A is the axion field, H of t is the Hubble parameter that depends on temperature, and MA of t is the axion mass that also depends on temperature. And this is a Klein-Gordon equation of a scalar field in a expanded universe, if you want, with mass MA. In this equation, we are dropping the gradient terms, which will be like the Laplacian here, because we're assuming for now that the axion field is constant in space, meaning it's the same in every space point, and we'll see what happens if it's not. So at the very early times, only these two terms of the equation matter, because the Hubble parameter is much bigger than the axion mass at high temperature. First, because the Hubble parameter is bigger than the axion mass, also at zero temperature, but in any case, at high temperature, this defect becomes perturbative, and the axion mass at high temperature goes to zero. So at very early times, at high temperatures, much bigger than the scale of QCD, only these two terms are important in this equation, and the equation is just a damped equation. And the solution is the axion field remaining at its initial value, which we parameterize as theta 0 times FA, where theta 0 is a dimensional parameter that is called the initial misaligned angle. So at very early times, for t much bigger than QCD, the axion field just sits at its initial value. As time goes on, the temperature drops, and these two terms at a certain point will become comparable at a temperature about lambda QCD. At this point, all three terms of the equation should be taken into account, and this is a harmonic oscillator with a down term that is proportional to h of t, that diminishes in time, and with a frequency given by MA. So at temperatures above lambda QCD, the axion field starts oscillating around this minimum with a frequency given by MA and with an amplitude that decreases in time because this is a damped oscillator with this Hubble friction. So these are coherent oscillations that are coherent oscillations, and their energy behaves exactly as cold dark matter, in the sense that the energy that is stored in this oscillation redshifts as the scale factor to the cube. These oscillations are interpreted as a bunch of axions at rest. So one can also calculate what is the energy density that is stored in these oscillations and compare the energy density in the oscillation with the dark matter energy density we observe nowadays. And the distillation is the dark matter intensity. So nowadays, times this theta 0 squared times FA over 10 to the 12 GV, and K and epsilon are order 1 parameters that depend on the detailed dependence of MA on temperature. And as you see by this equation, if you choose theta 0 over the 1 and FA over the 10 to the 12 GV, this mechanism, which we call design mechanism, because it's based on the fact that theta 0 is different from 0, this mechanism can account for the whole dark matter density. Just because if FA is over the 10 to the 12 GV and theta 0 is over the 1, then omega A is over the omega dark matter. So, as a consequence, this mechanism produces naturally order 1 contribution of the dark matter density also nowadays. So, in this discussion, we assume that the Axion field is constant in space, but in general it's not. And where it's constant or not depends on when the check-in phase transition happens. So, at very early times, high temperatures, the potential of the field that drives the check-in symmetry breaking is in its symmetric phase, just because of symmetry restoration at high temperature. At temperatures over the FA, there is a phase transition, and for temperatures more than FA, the scalar field that drives the symmetry breaking is in its broken phase. In this phase transition, the Axion field rolls down in different points, in different directions, in different points in space, just because different points are causally disconnected between one to another. And so, after the check-in phase transition, the Axion field has, in general, random fluctuations over what's now the observable universe. As a consequence of the check-in phase transition, actually, therefore, the Axion field is not really constant in space, but it has random fluctuations. So, where these fluctuations are important or not depend on when this check-in phase transition happens compared to inflation, particularly if it happens before or after inflation. And depending on if it happens before or after inflation, there are two different dark matter scenarios. So, first of all, suppose that the check-in symmetry is broken before inflation, and it's never subsequently restored. Meaning, FA is bigger than the maximum between the hubble during inflation and the temperature overheating. So, the first condition is to ensure that the check-in is broken before inflation, and the second that it's never subsequently restored. So, in this case, whatever are the initial conditions of the Axion, Axion field, also if these initial conditions are space dependent, due to the exponential expansion of the universe during inflation, all spatial Axion fluctuations are smoothed out over distances which are much bigger than the Hubble horizon at the end of inflation. If you want, the Axion field gets smoothed out and becomes constant over distances which are equal to the number of e-voltings the half-wall after inflation. As a consequence, for all practical purposes, the Axion field can be considered just constant in space in the scenario, and therefore it holds the discussion of 2 slides before, in which the Axion field is actually constant in space, and the only contribution is coming from the misalignment mechanism, where the Axion field oscillates around its minimum with agreement frequency and decreasing in time. However, this contribution, as we said, depends on the initial misalignment angle, and therefore is not just calculable as a function of the random parameters, or if you want it, just as a function of the phase. Depends also on this initial misalignment angle that is a cosmographical property, meaning depends on the initial Hubble touch of the universe. Different Hubble touches will have different initial misalignment angles, and we have in principle no way of knowing which misalignment angle was chosen by our touch. So in general, this theta 0 is not known in principle, and therefore the scenario is not really predictive. If you want, you can say at most that since the axion field is periodic, theta 0 should be less than pi. And so in order for the axion to make up the full relic density, FA should be bigger than 10 to the AGV just by putting FA inside this formula. But in general, all possible values of FA that are allowed by astrophysical constraints can be obtained in this equation by just choosing appropriately theta 0. And also theta 0 much smaller than 1 or close to 0 is not really a fine-tuning problem because there will be anyway some patches in the universe where theta 0 is so small. Of course, these patches will be much less frequent where patches in which theta will be is close to 1. But anyway, it's not a problem if theta 0 is chosen close to 0. As a consequence, this scenario is not really predictive because the dark matter relic density depends both on the Lagrangian parameters and on cosmographical property. On the other hand, if the Page-Green symmetry is broken after inflation, and or is subsequently restored, meaning FA is more than the maximum between the Hubble inflation and temperature or 18. So in this case, the axion field has random fluctuations over the observable universe as a result of the Page-Green symmetry breaking. And you can show that there are two contributions to the dark matter relic density. The first is the line contribution with theta 0 given by the average of all theta 0s that can be assumed in one Hubble patch, which is just 2.2 because the axion field is periodic. If you want, in one Hubble patch, the axion field will be periodic, and we will have a random fluctuation and an amplitude which is between minus pi and pi, and in average its value will be 2.2. But on top of this, there are extra contributions that are coming from the decay of topological defects that are stored in the axion field, and are called cosmic strings and domain walls. And on this, there are still larger possibilities. So in this scenario, the total dark matter contribution will be the sum of these two, and since both are positive, the dark matter density will be in general bigger than that just corresponds to the line contribution with this value of theta 0. And so the axion decay constant that is needed in order for the axion to make up the full rectangle in this scenario will be smaller than the decay constant that is connected to the only misalignment mechanism with this angle, and so smaller than about 10 to the 12 dB.
So where's that? Sorry, I went by very fast. Where did that 2.2 come from?
Yeah, so this 2.2 is a statistical average of the values that can assume the axion field. So essentially, is the average of theta squared between 0 and pi, if you want. Or so essentially, the axion will have
that's the uniform. This is the average of the uniform distribution because the potential doesn't matter at all.
As a approximation, it doesn't matter. Then this takes also into account the potential. So this will be by something. So if the potential is just quadratic, this is like pi squared or something. But if you also take into account the form of the potential, it's about 2.2. So this is just a statistical average of all the theta 0 squared values that can assume the axion in one Hubble patch. Yeah, so I was saying that contrary to the previous one, this scenario is predictive because in principle there are no free parameters from initial conditions. So contrary to the previous one, where there was theta 0, there will be just one value of FA, or just one value of the axion mass, such that the QCD axion makes up the full relic density. In the previous case, instead, we have a lot of values of FA such that the QCD axion makes up the full relic density just because we have a freedom in the system. In this case, there is no freedom, and there will be just one value of the axion mass such that the QCD axion makes up the full relic density. And knowing this value is very important, not only theoretically, but also experimentally, because the Axion experiments are really sensitive to the axion mass parameter. And so telling the experimentalist what is this value can narrow down the window in which experiments search for the axions, and could save us a lot of time and money in the search and the discovery of this particle. Also, if the axion is found at this particular value of the mass that is predicted by the scenario, this is a very optimistic view, but we will have an explanation of both the Strong problem and the dark matter, but also we'll have some angle in the OV universe because we could say that the scale of inflation will be bigger than the axion quantum. So calculating the dark matter contribution in the scenario is theoretically very motivated, and will be our focus. So as I said, in this scenario, the axion field has random fluctuations over the observable universe as a result of the preference transition. And since it's also periodic, there will be general configurations where the axion field erupts non-trivially, the fundamental domain is 0 to pi, like in this blue circle. Then, by continuity, if you shrink this circle to a point, there will be at least one point inside the circle where the axion field assumes all values between 0 and 2 pi, or if you want, where the axion field is not defined or singular. And if you do the same reasoning in the whole space, you will see that there is a line of points in which the axion field is singular, and such that the axion field gets a phase of 2 pi when constructing a loop around this line. So these configurations are possible configurations of the axion field because it's periodic and random, and are called Axion Strings, and are a kind of topological defect. So these strings have a calculated thickness that's called string core, and is of the order of the inverse of MR, where MR is the mass of the degrees of freedom that you recomplete the axion theory. So, for example, if you recomplete the axion theory with a complex scalar field with a maximum half potential, of which the axion is the angular variable, this MR is the mass of the Higgs mode of this maximum half potential, which is massive, of course. And if you take the Porty coupling of this maximum half potential to be over the one, this radial mode mass, which is essentially the square root of the coupling times the web, this radial mode mass is also of the order of the web of the maximum potential, which is a thing. So in a region of order and a maximum with distance of order maximum -1 from the center of the string, the distribution and Gaussian motion of the view with this potential have the radial mode on top of the potential in this region. Then the radial mode goes on the bed very large distances from the center of the string, while the angular mode wraps non-trivially the domain around the string. And these are typical solutions of the classical equation of motion of this kind of theories. So these Stoichiometric solutions, Axion Strings, have a lot of energy, and this energy is always computed through the so-called string tension, that is defined to be the energy of this configuration's per unit length. And this energy can be computed in simple cases and is given by pi, fa squared, times the log of the ratio between the distance between two strings and the string core size. So, first of all, the string tension can be divided into two pieces. The first piece is pi fa squared, and it's a contribution that comes from the fact that the radial mode is on top of the potential in a regional space over the minus one from the center of the string, and the radial mode being on top of the potential gives a contribution to the potential and energy density, just the potential energy density. On top of this, there is a logarithmic contribution given by log of the distance between strings and the string core size, and this logarithmic enhancement derives from the fact that the energy density of the strings is actually, of one string that is actually logarithmically derived. So because you can show that these string configurations behave exactly as a charged wire in electrodynamics. So the energy density for one string is logarithmically divergent with the distance from the center of the string, just because the axion was like what the integrand was like 1 over r to infinity. So in the integration you have a logarithmic divergence, and and this logarithmic divergence is cut off by the distance between two strings with opposite orientation, or if the strings form a loop by the radius of the loop. So in the early universe, as we will see, this distance is the distance between two strings with opposite orientation, or the radius of loops will be of the order of the Hubble distance, and so this log will be the log of mr over h, just because this one. So the situation is the following: after inflation, there is a U1 that you're going to integrating, and in general, a configuration of Axion strings will form because the Axion field is periodic and it has random fluctuations. So, although these strings are stable by themselves, when taken alone, when they are taken together, they can interact with each other. They can form loops that can shrink, and in a process that's called recombination. And the result of this process is the reduction of the string length, the reduction of the string energy, and the conversion of the energy that's stored in the string in strings into radiation. And this radiation is then interpreted as Axion particles, and these Axion particles make up a part of the relic density, of the dark matter relic density we observe nowadays. So, once these strings are formed, they are thought to go in a so-called scaling regime, where there is in average one string per Hubble volume. So, so the reason is the following.
So I can ask you a question about that? I mean, I thought that a few years ago, Hitoshi Moriyama and Jing Shu, they had a paper about this, and that questioning this Kibble, picture for string formation, generally for defects. So apparently, in condensed matter physics, people realized that the forming defects was more efficient than was predicted by this kind of mechanism. I don't remember the details, but I remember. Are you aware of this work?
No.
Yeah, so you should probably look at it. I mean, their claim is that the standard Kibble mechanism for these things grossly underestimates the number of topological defects.
So you say that the density of topological defects
is much higher. That's my memory, so don't quote me, but you should look at the paper.
Yeah.
It's a couple of years ago.
I can believe that it can be that the estimate of the initial number of defects is different. But I guess that the results I will show you don't really depend on how many defects are produced by this Kibble mechanism, because we will see that. so the results will be independent of the initial density of the defects. So, yeah.
Okay.
So, but I can probably do that in the debate. So, once these strings are formed, they go into a so-called scaling regime, where there is a constant number of strings per ball volume, and a personal number of strings per ball volume. So the reasoning is the following. So as the upper parameter diminishes, the upper horizon grows, and strings that were previously disconnected between each other come into each other's horizon. As a result, they will kind of annihilate, will have some dynamics, and you expect them to go in a sort of equilibrium, where the rate at which strings come into each other's horizon is the same at which the rate at which strings shrink, in such a way that the number of strings per volume remains approximately constant in time. Also, this regime, where the number of strings per volume is above constant in time, is expected to be an attractor, meaning is expected to be independent of the initial string density. Supposing that the initial string density is very low, for example, there is one string over 10 ball patches. These strings are causally disconnected, so they cannot interact between each other, they remain frozen. And so while the upper parameter increases, the upper horizon increases, the number of strings per volume will increase. On the other hand, if there are too few strings, too many strings per volume, meaning there is a huge density, a high density of strings per volume, this recombination process is actually very efficient, and strings annihilate very fast. And so the number of strings per volume decreases. So we expect a first approximation that actually this regime is actually independent of the initial string density, and so as we were saying, probably will not affect the results. Indeed, I show you in this video what I was telling you before. So this is the Hubble volume that increases in time, and this is a configuration of Axion strings. But although total length decreases, the number of strings per volume stays approximately constant in time. So as you see, the dynamics of strings is very complicated, and as a consequence, probably this kind of numerical simulations are needed, because analytic understanding is very difficult to have at this stage. So this scaling regime, where there is approximately a constant number of strings per volume, lasts for a long time, until the time of the QCD defects transition. So at this time, the axion mass turns on, also the axion potential turns on by number 2 because it QCD effects, and the points in space where the axion field is pi, that are present because essentially the axion crops all values between 0 and 2 pi. These points where the axion field is pi have more energy compared to the others, because at these points the axion field stays on top of the potential that indeed is important because of the effects. And these points form a two-dimensional surface that's called the main wall. For a system, and this surface has a tension, meaning an energy per unit length that is bigger than the energy per unit length per unit area that's outside the surface. So, for a system of strings and domain walls, it's more convenient to annihilate and emit the energy that is stored in the strings and the domain wall tension into waves. And so in order one Hubble time, the system of strings and domain walls completely shrinks and emits the energy that's in the sort of strings and domain walls into radiation that is again interpreted as Axion particles that make up another contribution to the Axion wave density groups around waves.
Sorry, can I ask you a question? So before you were there was this contribution, what you called it the string tension, that went like log separation. I mean, that's clearly a long-range force, right, between strings.
Yes.
And so, I mean, what you're saying here is that at low temperatures, in some sense, that force is becoming confining, in that it's making it's making these domain walls. But at high energies, it should also still be important, right? It's a long-range force.
Yeah, of course. No, then here there is an additional force. At these lower energies, there's an additional force that is the force of the domain walls. So that is another thing.
You think it's a different thing? Okay, but then first let me just ask about the long-range force. I mean, this log d term in the string tension, I think it's a little bit misleading to think of it as a string tension term, because it really is a long-range force between the domain walls, right? No, strings. Sorry, you've got too many solitons in here. So is that force? Does that force play an important role in the string dynamics at high energies before you get to this?
Yeah, of course it's very important.
So okay, so in other words, your simulations, you're taking into account the fact that there's this attractive force.
Yeah, automatically taking into account because we are solving equation motion.
Okay. Right.
Then
but you're saying this is not. I somehow thought that this is somehow the statement that that this force, in some sense, confines or something. It's not like that.
No. So I guess the statement is that at this time, so this potential goes on, and so there is an additional force that tends to diminish the area of these domain walls. So there will be points in space where the Axion field is like on top of the potential, and the fact that these points have more energy induces a force on the strings that tends to diminish the area of the surfaces, and this force tends to annihilate the string.
What's the force law? Is it linear?
It's given by so.
How does the force depend on the distance for two long parallel strings?
No, so it's essentially proportional to it depends on the tension of the main walls. So essentially, it's
but I'm asking about the distance dependence.
Yeah, it's
on
proportional
the distance
to the area of the main walls.
Right, so it's proportional, so it's a linear force law.
Yeah.
The confining force law. My guess is that you could view this as somehow the confinement of the strings, but it's okay.
Yeah,
I see it as somehow that, if you in confinement, you have a Coulomb law that turns into a linear force law, right? Here you have one less codimension because you're talking about strings, so you start have a 1 over r law, right? It turns into a confining law, which is linear. So, anyway, it's just a picture. I think it's okay. I think it's the same thing as what you're saying.
Okay. So the result of this process is the annihilation of the string domain wall system. So, and summarizing, therefore, the picture is the following: for temperatures and Hubble bigger than order of A. A configuration of Axion Strings form as a consequence of the phase transition. At this time, the log of Mar range, which you should interpret as the log of a fair range for decoupling over the 1, is between 1 and 15. So the strings then go, are thought to go in this scaling regime, where there is approximately constant numbers of strings per volume, and this regime lasts a long time until the time of the phase transition, when temperature is over number QCD and Hubble is over the Axion mass. And at this time, these domain walls form and annihilate under the effect of their own tension. And at this time, the log of Mar range is about 70. for the values of a fade that are allowed by as visual constraints. At this time, the domain was annihilated the string system, and as a consequence, after this time, there are no more strings for domain walls. During this whole process, the system of strings and domain walls emits Axions, which make up a contribution of the relic Axions. So nowadays, which should be updated to the misalignment, to the average angle misalignment contribution. So our focus will be just the first part, so not the main walls, will be the understanding of the scaling regime. In particular, will be the understanding of the string dynamics and the emission of Axions from strings. This will be important because not only will give us a contribution to the Axion mathematical density so nowadays, but also because we'll set the initial conditions for the study of the system of strings and domain walls. It's very difficult to believe that one can study the system of strings and domain walls without knowing the initial conditions that come from the annihilation from the scaling regime.
And this action, immediate action, will be added to the whatever the 2.2 contribution. But here you annihilate in the way you somehow remove the largest theta equal to pi contribution.
So you get
right? Here you string annihilate. Don't you just remove this large theta part? Theta equal to pi part.
Yeah,
so is that still valid?
Yeah, so
statement that it add? Well,
no, the statement that should be added is like a bit made up, meaning that in principle you should run, you should solve the equation motion from the beginning to the end without doing a distinction between average angle misalignment, strings and domain walls. But for the sake of simplicity, it's very useful, and it has been done in the past to divide these contributions into strings and domain walls, and average angle misalignment. But in principle, yeah, you're right.
Is that a approximation valid or not?
Sorry?
Is it really valid? Say?
Yeah, in a sort of approximation is valid as a all-in-one estimate, but then if you want to do very precise calculation, you have to in principle study.
Just remind me, isn't it true that, so there's the QCD phase transition temperature, that's also around the scale where the axion starts to oscillate, isn't it? Or
yeah, so
they happen at the same scale.
They happen at the same scale, but so this not exactly at the same scale. It depends on a phase. So it starts oscillating when H is awarded MA.
Right.
And
oh, sorry. Right. So which one is bigger? So sorry, they're not the same then. So which happens? So for the range of FA of interest,
I guess
when does it start oscillating?
At a bit higher temperature.
At higher temperature. So then the point is that this string annihilation is happening at near the QCD scale, but they start oscillating during the scaling regime, I guess.
Well, it depends on the phase. So this relation is so gives this with this tilde means that it depends on the phase, but in general, yes, a bit bigger.
Yeah, for order 1 theta, it's so that.
No, but his worry is that in principle, one cannot really distinguish between the average angle of alignment and the
yeah, I get that, but I was just trying to understand first. So during a lot of the scaling regime, actually the axion, in some region where I can think of the axion field as being homogeneous, it's actually oscillating.
Yeah.
Right. And then, then the worry is that somehow you're getting rid of all of that when these domain walls
yeah, so it can already be contribution from domain walls and in a sense cannot be distinguished from so it was also part of the average angle, if you want. So the two cannot be separated.
And also just vice versa, kind of the oscillations don't affect the domain wall dynamics. The fact that actually
it may be. So indeed, this part in information domain walls and etc. has not been studied in this work. So we're just studying this first part. So when just before the main walls form. But yeah, there are many caveats. So first, the fact that you cannot really distinguish between domain walls and average angle. Then the fact that domain walls can affect the oscillation. Yeah. So for now, I guess that it's still open problem. This question, but as a first approximation, you can say that at least there will be a contribution coming from like the waves that are produced in the same regime, because these are waves that are produced, and you expect that these waves just propagate without interfering with anything. And these waves anyway are there and they will produce at least a part of the dark matter. Then on top of this, we have to calculate also what happens afterwards. Okay. So let's go to string dynamics. So as I said, studying the dynamics of Axion strings is very hard to do analytically. You can have some understanding of doing that with solving the equation motion for particular symmetric configurations, for example, infinite long strings. But having an understanding of this process is very difficult. Also because these are time dependent, and you cannot really solve the equation motion with a time dependent solution. And so we resort to numerical simulations. So which can give us not only a qualitative but also a quantitative understanding of the dynamics. So we approach the problem by considering a UV completion of the Axion theory. And this UV completion is a UV completion made by a complex scalar field phi, which has two degrees of freedom, a radial mode which has mass mr, and the Axion field, which is the angular variable, which is massless at these high temperatures. And the potential is just an experimental potential. So we solve numerically the equation of motion of this system in a lattice, which has about 1,000 points per side, and which is recently upgrading to 4,000 points per side, and with periodic boundary conditions. So, so the equation motion is solved in a parallel code, which is run on a cluster, and actually is a very big cluster because so the code has been parallelized in different nodes. In particular, for this kind of simulations, order 1 terabyte of RAM is needed to solve the equation of motion and to store the reads. So the problem of these simulations is that there is a huge separation of scales. In particular, there are two scales that are both solved at the same time, and which are very different. So, the first scale is a macroscopic scale, and is the size of the string that is of the order inverse of the mass of the heavy modes that we compute the Axion theory, and is over the order of 1 over F. So this is a macroscopic scale that is the distance of new physics. On the other hand, you should also resolve another scale which is much larger, and it's the Hubble scale. It's a cosmological macroscopic scale, and is given by a QCD transmission by the Planck mass over lambda QCD squared. Of course, these two scales are one macroscopic and macroscopic, and therefore are very different. And the ratio for the values of Fa that are allowed by Axion strings is bigger than 10 to the 30. So if you want strings that have distance over the Hubble distance, for example, the transition, are 10 to the 30 times more distance than they are thin. The ratio between the distance and the thickness is 10 to the 13. And the solution is even worse because at first approximation, the property of the strings depend on this ratio, whether you're on MR range or with this. For example, the string tension depends on this ratio, because we said that the string tension is given by F squared times the log of the ratio between distance and string core size, and there's an explicit dependence on this ratio. And if you take this with 10 to the 30, the string tension will be 70 times bigger compared to the case where you take this log, this ratio over the 1. So at the first approximation, we expect that the dynamics of the strings actually depends on this ratio, FA over H. So as time goes on, we expect that actually the dynamics of strings changes depending on this ratio. And the fact that physics depends on this used separation of scales actually makes the simulation really hard. So first of all, there should be a few lattice points per string core, meaning the string core should contain some lattice points, otherwise you cannot really resolve where the strings are. On the other hand, there should be a few couple patches inside the box. Otherwise, you're not simulating anymore if you big universe, but will be fine by effects. So if you want, if this cube becomes bigger than the box, then you're not simulating anymore infinite big universe, but a three-dimensional torus, which is not physical. As a consequence, the log of the MAR range, which should be 70, is bound to be less than the log of the ratio between the side of this cube and on the horizon of the circle, and this is log 6. Of course, much less than 70 if the number of points is about 10 to the 3. However, the situation is not so desperate because still we can take advantage of the scaling regime if it exists. So the idea is that simulations can run between log of MAR range over the 1 to log of MAR range over the 6, just because of this constraint. But since there is still enough time in this range, we should be able to understand the dynamics of the strings. In particular, we should be able to understand the properties of the scaling regime, in particular the parameters that characterize the scaling regime. For example, the number of volume and the rate at which axions are emitted. And once these parameters are understood, we should be able also to extrapolate if these parameters are actually independent of time, or have a time dependence that is understood. We should be able to extrapolate these parameters all the way to the physical point that corresponds to log of MAR range equal to 70. So although this extrapolation seems crazy, because we're separating something that's known from 1 to 6 up to 70, in principle, this expression is doable because in principle there are strong arguments that the scaling regime that is approximately scaling grind, so depending on time, exists. So just to say, usually in literature, in this kind of simulation, it's used something called a fast string trick, in which one changes manually in time the radial mode mass. In the sense that instead of evolving the equation of motion, in which the radial mode mass is a fixed parameter, usually people change manually the dependence on time of the radial mode mass, making it diminishing in time as 1 over t to the 1/2, meaning as the scale factor in relation to elimination. In this way, the string core is fixed increases in time in physical coordinates, but is fixed in conformal coordinates. And this trick is helpful because it allows to reach scale separation of log MR range from 1 to 6 with much more cosmic time between initial time and the final time. So just because the way of MR, in which MR changes in time. So since there's much more cosmic time, there's more time for the string network to reach the scaling regime, and so this attractor can be understood better. Also, the radiation that are initially present in the initial condition will be more shifted because there is more cosmic time from initial time to final time, and so the energy in this spectrum will be better. However, this trick is not physical because you're changing the order one, the equation of motion, particularly your inclusion dependence on equation of motion, which is not physical. So you shouldn't trust the results using this trick. And indeed, we did the analysis both using this trick, and the results are order one different quantitatively, but they are qualitatively comparable. Meaning, the physics is qualitatively the same. So let's go to the main topic. We want to determine, first of all, the existence of the Attractor solution, meaning we want to see that the different initial conditions tend asymptotically to the statistical properties of the network for different initial conditions tend asymptotically to the same asymptotic value. Once this attractor is understood, we want to study its properties. Particularly, we want to study the average number of strings per volume, which, as we said, is expected to be about constant in time. We want to understand how the energy from strings is emitted to Axions, and in the end, we want to understand the spectrum of Axions emitted. And all these properties, which should have a well understood time dependence, would give us the number of Axions produced by strings. So first of all, we want to show the existence of the Attractor, which means that we want to show that different statistical properties of the network are free from initial conditions, and they tend to converge to the same asymptotic value independently of how initial conditions are set. So we show that many statistical properties of the network tend actually asymptotically to the same value, but here I show the so-called scaling parameter that we define psi, and is defined to be the number of strings per Hubble volume. And we want is the string length in one Hubble volume in units of the Hubble radius, average over all the Hubble volumes in the universe. So for example, this configuration has a scaling parameter psi equals to 1, just because it's just one string in one Hubble volume that has a length equal to the Hubble radius. This configuration of psi equal to 2, etc. So in this plot, I show the evolution of the number of strings per Hubble volume as a function of time, that is represented as log of MRH, or if you want log of FARH, for the fat case, where we change minorly the MR in time, making it diminished in time, and in the physical case where MR is a constant. So you see that even if the initial conditions range over a wide range of orders of magnitude, the asymptotic behavior of the number of strings per volume actually tends to be the same up to 10% difference. And the convergence is much better seen in the fat case compared to the physical case, because as I said, there is much more cosmic time from initial time to the final time, in this case compared to this, just by the way MR changes in time. Although here the convergence is better than this, also here the convergence is clear. So although these different initial conditions tend asymptotically to the same value, actually this value doesn't seem really to be constant in time. And indeed, if you plot this plot with the linear axis and the y-axis, you see that indeed, although different initial conditions tend to the same value, this value actually increases in time linearly with the log of time. And But in particular, this logarithmic growth is a scaling violation of the scaling regime. There is a logarithmic violation of the number of strings per volume, which is not constant, but increases the logarithmic in time. And it's much better seen in the fact case compared to the physical case. And what actually tells you that this logarithmic growth is actually a physical property of the attractor, meaning it's not a transient, but it's a property of the attractor solution, is the fact that there are initial conditions where the number of strings per volume is first very high, and then it decreases, and then it increases again, showing that this increase is actually a property of the attractor solution, and it's not like a transient, and these lines are going to saturate at a certain point. So the fact that the conversion first goes down, then goes up again, is a hint that this property is a feature of the attractor. And so this logarithmic increase is compatible with the form of this with the dependence of this form, psi equals to alpha log over MRH plus beta, where alpha is a parameter that actually doesn't really depend on initial conditions for the approximation, while beta depends on initial conditions, but at log values of log, only alpha is important. And if you really believe that these lines continue to be linear all the way up to log of MRH equals 70, then the extrapolation of the number of strings per volume, if this is linear, gives that the number of strings per volume at the QCD transition, where MRH is log of MRH 70, is about 10 instead of over the one. It can be done in the simulations. So this will be. This means that we 10 times the strings that are present in the simulations. So the 10 times more energy, so 10 times more Axions produced. So we also have probably some explanation about this logarithmic increase, but that it may be related to the fact that the tension of the strings depends actually on this ratio. But since this increase is also present for local strings where there is no log in the tension, we refrain to give this interpretation, to connect this interpretation to the tension of the string.
So this log increase is also present in what?
In local strings. Local strings are strings that arise from a local.
They don't have this long range.
They don't. But even if they don't have this log, actually they also show this log increase, which is a bit puzzling because in that case the tension doesn't depend on log because the energy is only localized around the cores. And so anyway, this just to say, we also studied the distributions of loop and non-strings, and we showed that so non-strings are a definition of strings that have length much bigger than the Hubble horizon. For example, it's a long string because its length is much bigger than the Hubble horizon. While loops, by definitions, are strings that form loops which have length smaller than the Hubble horizon. And we showed that in the scaling regime, 90% of the length is stored in long strings, and the remaining 10% in loops. And these loops form a scaling invariant distribution, where there is a constant number of loops for the decade of length. So, for example, if there are two loops with length L, there are two loops with length L over 10, etc. And so they follow a scaling invariant distribution. Also, we show that this 90% and 10% is a scaling a probability that is independent of time. Meaning, at any time, there are always 90% of strings that are of length that is stored in non-strings, and 10% of length in small loops. And this ratio is actually 90-10 for all time instances. Which also means that the logarithmic increase in the string length is equally distributed in long strings and small loops. If you want, as time goes on, the number of strings per volume increases both for long strings and small loops, and this is a hint that this logarithmic increase is a property of the string regime. And here are more details which we will skip. So from the scaling parameter, you can calculate what is the energy stored in the configuration of strings, and which is given, if you want, by psi mu effective over t squared, where t is a cosmic time and mu effective is an effective string tension, that is the total energy of the strings over the total magnet. And by taking the derivative of the equation, you can get the rate of emission of energy from strings to radiation in order to maintain the string regime. And this is given by psi mu effective over the cube. And this can be actually divided into two parts. So this rate of emission can be divided into the emission of the axion mode, which is the one with zero freedom, the mass of zero freedom, and the emission of the radial mode, which is the mass of zero freedom. So the energy stored in strings diminishes and is emitted into axions and radial mode, and the rates are parameterized by these two things. So the first approximation, you expect that since axions are massless and radial modes are massive, first approximation, you expect that all the energy that is emitted by strings goes into axions, because they're masses and much easier to excite compared to heavy radial modes. So you expect that the first approximation, most of the energy goes into the massless modes. And here I show, as a function of time, the emission of axions compared to the total emission. And you see that a bit passively, there is a non-negligible production of heavy radial modes. If you want, 80% of the energy that is emitted from strings goes into axion modes, but there is still a 20% energy that goes into radial modes, meaning these modes are really massive, meaning, for example, at the final time, their mass is e to the 6, which is about 500, bigger than Hubble. Although they are so massive, 500 times bigger than Hubble, they are still produced in a non-negligible amount. So, as you see, this thing will have some connection with the spectrum. So the last thing really we need to know is
you're trying to describe things really well below the scale MR, right? I mean, you eventually would really like to be able to describe things near the QCD phase transition, whereas MR is 10 to the 12.
Yeah. As I said, there are problems with that.
Well, I know you can't. I understand that you can't do those simulations, but so that it's very hard to believe that, you know, at the QCD scale, 20% of your energy is going to be going into exciting modes that are 10 to the 12 GeV of mass. So I just wanted.
I agree, and indeed that the thing you're saying would mean that this curve actually goes to 1, meaning all the energy goes to axions, and it's a possibility. And actually, it's the more.
Also, I mean, it's somehow this is crying out for some sort of an effective field theory treatment, right? I mean, somehow
of course,
the way you would really like to handle this huge separation of scales rather than simulating it is to figure out how to describe the strings from a long distance point of view, right?
Yeah, indeed the people try to do that. They try to couple strings described by numerical strings coupled to form of the axion field. So, in an effective description. But the problem is that this description breaks down when strings have
when they cross, right?
Yeah,
you have to
when
find
they
out
cross.
what the rules.
So although this description is completely valid when they don't cross, when they cross, the description is not valid anymore, and so you have to parameterize the crossing, and you by parameterize the crossing, except for that, you may introduce some. But as I said,
that's what you would have to do. You'd have to figure out from short scale simulations what happens when strings cross, and then somehow incorporate that into your simulation on larger scales.
Yeah, we are not at the stage where we are just at the stage of just simulating the most we can do.
Yeah.
just hard simulations.
It just seems like this result cannot be, extrapolated.
And the course that has very high energy density than the temperatures, so it's not
Well, but he's saying radial modes. I mean, well, that was actually my thought, is that, when you're simulating the whole thing, how you divide things into radial modes versus other kinds of modes is actually ambiguous, right?
Yeah, so yeah, it's ambiguous.
It's not really well defined.
Okay, if you're very far from a string, it's not ambiguous. If you're
using effective field theory, if you have some systematic way of taking that into account, but if you're just looking at this simulation and trying to draw a line somewhere, you have to, it's ambiguous, right?
Yeah, so the distinction between radial modes can only be done if there are also strings there, essentially. So because the strings will have the radial mode on top of the potential near the string. So if you go sufficiently far from the string center, so contribution to the strings of the radial mode will be smaller, and sufficiently far from the string center, you can like the distinction between the part of the radial mode that contributes to strings and the part of the radial mode that contributes to the waves. So this distinction is the way we. So this energy emitted is, if you want, looking at the system very far from the string center in which this distinction can be made.
So sorry, so maybe I didn't really understand. So how are you defining the radial part? How is the radial part defined?
The radial part of
the radial emission? How do you count what part?
It's defined by the following. So we look at the energy density of the radial mode outside the string cores. So this energy density is the energy density per r of the radial mode. So if you want 1/2 r dot squared plus 1/2 radius of r squared plus the p of r, we're very far from the string center. This is the energy density. And if you go outside the string center, this doesn't get any contribution from the strings. But it only takes into account the radial waves that are present. And also we checked that this energy density redshifts as it should, meaning redshifts as matter. So it's a way to check that it's consistent. Anyway, and while this axion is again the axions, so the kinetic energy density of axions outside the string cores. So these are a bit of so you cannot really take the gradient energy density, because the gradient energy density takes into account also of the gradient of the string tension. So for the axion, you just take the kinetic energy density and you multiply by 2.
You're saying that this excitation, this piece which you identify with the radial excitations is redshifting like matter, so suggesting that it's some persistent oscillation. But I mean, physically, we would expect that for example, the quantum lifetime of one of these radial excitations, a single quantum of that would just decay.
Yeah.
And on this time scale, very short.
They decay immediately.
And somehow in your simulation, these guys are persisting, even though the nonlinearities that cause that decay are certainly there in your simulation.
Yeah.
Right?
But this anyway is the instant emission of radial modes. So is what is instantly produced. So it's not like so this is like energy density radial modes at one time minus that at the times before divided by with property scale by scale factors. So this is not the energy that's needed for initial time to final time, but just what was instantly emitted. So it already takes into account the emission. So
it's just mysterious, so it shouldn't be highly suppressed.
So
like
as I said, for approximation, you expect that it should be highly suppressed when this log is 70. But in this case, log is
highly suppressed and that log is 6, I think. 6 orders of magnitude, well, whatever, not 3 orders of magnitude, whatever, you know.
So the separation is the 6, which is 400. So the separation is 400. So if you want...
With the QCD scale, I don't think there are many Z's around.
It's 10 to the 30.
Okay.
As I said, the course there has very high energy density, even though the temperature is low, so it's not clear that it cannot reduce the ADO.
But he's saying that this, okay, maybe, but then would you then expect it to scale like some bulk distribution of...
I don't know how it works here, but
Yeah.
it's just, well, I don't have any intuition.
But anyway, we will see that there's a emission of radial modes, heavy radial modes, is connected to what comes next, which is the Axion factor. So to say, so the last ingredient we need to know is the Axion spectrum, which is defined to be how the energy in Axions that is this one is divided into different frequencies. So the Axion spectrum is below A indicated T, and then is the energy spectrum of Axions related with time, and here there is a picture. So we have some practical expectations for the spectrum. First of all, the spectrum should have natural cutoffs at omega over the Hubble and omega over the MR. So this cutoff means that there should be a cutoff for omega smaller than the Hubble, just because of causality. You cannot emit wavelengths that are bigger than Hubble horizon. On the other hand, you should have a cutoff for omega bigger than MR, because MR T-1 is the smallest scale of your problem, and so you cannot emit the momenta that are bigger than MR. Then we should expect that the spectrum has a peak at omega over the Hubble, because strings are curvature over the Hubble. And so since they are curvature over the Hubble, we expect that the average wavelength that's emitted is over the inverse curvature. In between, the spectrum is usually approximated with a power law, which we call 1 over Q, where Q is a dimensionless number, which determines the hardness of the spectrum. Particular Q determines if the spectrum is UE or IR dominated. So in the literature, there have been some proposals for this power Q. Q could be bigger than 1. In this case, the spectrum is soft, and the average wavelength is over the Hubble. So the spectrum is, for Q bigger than 1, the spectrum is completely peaked at the horizon scale, and is IR dominated, and the average wavelength is essentially the Hubble horizon. This Q bigger than 1 is actually expected for a log of MRH much bigger than 1, because for these logs, the system of global strings tends asymptotically to the behavior of a system of local strings, and the system of local strings, the loops of the systems bounce many times, and while bouncing many times, they emit wavelengths that are only wavelengths that are of order of the initial radius, which is upward. On the other hand, there have been some other proposals, so this is actually further complicated. Then there are other proposals that say that Q is equal to 1, but the scheme in this case, the spectrum is hard, and expression, there's a expression of the average wavelength of a factor log of MRH, and if Q is more than 1, the spectrum is UV illuminated, and the average wavelength is over the FA, -1 size. And these three cases have a big impact on the number of Axions produced. So in this first case, all Axions are produced with a small energy, which is over the Hubble, and so many Axions are produced, each one has a low momentum. In the last case, the energy is stored in few Axions, each one has a big energy. So what actually is important in discussion is anyway only the number of axions produced is important and not the energy, another energy. Because although these axions are produced relativistic, because at high energy the axion mass is smaller, then the axion mass turns on, and the energy of all these axions redshifts. And as a consequence, although they are produced relativistic, they all become most of them become non-relativistic, and only their number is important and not their energy. So, in understanding the number density of these actions actually leads to the dark matter energy density, because in the energy density will be the number of actions times the pure mass. So here show the dependence of the number density on this Q compared to Q is equals infinity. And you see that if this Q is 1, then the number density is still suppressed of 10 to the 2. While if Q is more than 1, the number density is suppressed by much more than 2. And so therefore, understanding what is this Q is very important because it will be very different answers in the final number density. Particularly if Q is greater than 1, many actions are produced, each one has more energy, and if Q is more than 1, few actions are produced. So actually the simulations can calculate the axion spectrum, and therefore can give us the result for Q, particularly if Q is greater than 1 is more than 1. So simulations provide a total spectrum from initial time to the final time. Therefore, all the spectrum of all the waves that are emitted from initial time to final time, and the first ones are more shifted. And the spectrum looks like this. So I here plot the spectrum as a function of momentum, spectrum normalized by HFV squared as a function of momentum normalized by Hubble. And as you see, the spectrum has a peak a momenta over the 5 Hubble, and the two cutoffs that are theoretically expected, particular cutoff from momentum more than 5 Hubble, and another cutoff from momentum bigger than MR over 2. And this for log of MR equals 4. And as time goes on, for 5 and 6, you see that the peak of momentum over the Hubble remains at the same point in units of Hubble, and the two cutoffs remain at the same point, units of Hubble and MR. So in between there is a power law that is more and more evident. And as you see, for times bigger, as multiple times where the separation between Hubble and MR is smaller, these two cutoffs cannot be really distinguished. So from the total spectrum, one can calculate the instantaneous spectrum by just taking differences. And if you want the spectrum, total spectrum one time minus total spectrum another time, and the several one are shifted. And these are the instantaneous emitter spectrum as a function of time. So this is early time, this is late time. And as you see, initially, so the fact that I have a peak at momentum over 5 Hubble, and then I have the cutoffs we said before. But asymptotically, at late times, the spectrum actually has develops a power that can be computed in the simulation, and which, as I said, we called Q before. So one can measure this power, and by doing just a linear fit of this final time where this power is evident, and it turns out that this power is smaller than 1, meaning that 0.75 with an error of 5. As a consequence, the spectrum is UV dominated, and few axions are produced, and all these axions have a big energy of the order of a fade or of the string size. So, and it's actually against the intuition that all actions will lose with moment over the Hubble. And however, this uncertainty is really large, meaning this 75 as an error of 5. So a small violation of the spectrum of this Q of the kind 0.7 plus 0.01 log cannot really be excluded. And this violation is not excluded by this formula, because for these values of the log, this 0.7 plus 0.01 log actually is compatible with this. But then if you extrapolate this small violation, if you extrapolate this small violation, it will lead to Q bigger than 1 at log equals 7. So although in simulation, where there is a small scale separation, the spectrum is denominated as a small violation, which actually we expect to be present, because also number of value as this violation, a small violation of this kind will lead to completely different results. So although the spectrum is illuminated at these times, a small violation would make the spectrum higher illuminated at the physical point. As a consequence, this cannot really be extrapolated well. And indeed, new simulations show that there is a dependence on this power on time. This is a simulation with 4,000 degrees, and as you see, there is a little increase of this Q, which actually is much bigger than 0.1, and this shows that actually there is a dependence on the spectrum slope on time, which makes maybe the spectrum more and more higher illuminated, but still is still pretty. And as a final joke, I want to show you the last slide, the different predictions from the Axions from strings, depending on the extrapolation of this power Q. So here I show the number density from strings normalized by h of a squared as a function of log of time, and the physical point is log equals 70, and this is a simulation. Of course, you have to extrapolate this line all the way up to here, but it's actually very unreasonable to think that without having theoretical understanding. So first of all, I show you as a reference the average angle misalignment contribution, which is just the axion field oscillating constantly around its minimum with initial value 0.2 squared. So as first approximation, you could just extrapolate this line linearly along, obtaining this result, although there is no reason to do that. If instead you take the result of the spectrum from the simulation, which told you that the Q was 0.75, and you extrapolated that value of Q, keeping it constantly between 0.7 and 0.8, you get that the number of actions from strings will be much less than the misalignment. And this is because all actions are produced, few actions are produced, each one is very energetic. On the other hand, if for some reason Q is equal to 1 or even to infinity, at large times, as is very expected, the number of actions from strings will be much bigger than the misalignment. And also, if there is this small violation, which may be present and cannot be proved by simulations, of the spectrum of the kind 0.7 plus 0.1 log, if extrapolated, this small violation of the constant from Q of Q gives a completely different result compared to Q plus constant, just because this violation is Q bigger than 1 at the log much bigger than 6. As a consequence, you see that there is still a huge uncertainty on the number of strings of actions from strings, and this uncertainty is just given by the fact that actually we don't know how to extrapolate this spectrum slope. And this uncertainty actually scans, so different operations scan different values of the axiom of number density from strings, and different operations actually don't agree for these values. And the main reason of the disagreement is the extrapolation essentially of the spectrum. So here, as a final, I want to show the prediction for the axiomatic constant for the bound coming from the matter of the closure of the axiomatic constant as a function of different extrapolations. So these are bound coming from the fact that if an upper bound coming from the fact that if the FA is bigger than its value, this means that more we produce more actions than the observer right master. So FA should be smaller than 1011 GV if you only consider this alignment. But you see that if really Q is equal to infinity at large times, FA should be smaller than about 10 to the 8 GV, which means that actually there is probably some tension with this cosmological bound coming from dark matter overclosure with the limits coming from astrophysical constraints. However, I'm not saying that this is the final result. I'm saying that there is still a huge uncertainty for the Axion strings. And this uncertainty is just given by the fact that we don't know how to extrapolate the spectrum. And once this extrapolation of the spectrum is known, we will be able to give a bound on the Axion data. And in some cases, this bound will be in conflict with astrophysical constraint. And in this case, if it's really true, the scenario will be actually without. So, basically, symmetry of inflation will be without. However, there is still a large uncertainty, which actually is made clear by the fact that different collaborations have different opinions. So, concluding, so we studied the system of Axion strings, which we showed are driven towards an Attractor solution. And solution, in this Attractor solution, the system of Axion strings shows a logarithmic violation, where the number of strings per volume actually increases logarithmically in time, and the small loops follow a scale invariant solution. And for values of the log, smaller than 6, there is a non-negligible production of heavy radial modes, about 20%. And this non-negligible production of radial modes is connected to the fact that you see that there is a UV dominated spectrum of small values for these values of log of our H. And therefore, a very high precision is required for a reliable extrapolation of the spectrum. And the next step is to investigate the violation of the spectrum. If you want to investigate how one can extrapolate reliably the spectrum power as a function of time. Once this extrapolation is understood, as I show you in this plot, one can give a more sharp prediction for the Axion relic density. However, for now, there are still large uncertainties that are essentially connected to the fact that we don't know a precise estimation of the time dependence of the Axion spectrum. Okay, that's all. Thanks.
Any more questions?
You're still going to be working on this?
Yeah. So the next step is to understand the violation of the spectrum. In particular, so independence of the spectrum on time. So if you can reliably extract the dependence of the spectrum on time, and you believe in your extrapolation, you are able to, in principle, make this contribution from strings. And then is so if you want, it's very important because, as I said, we give a bound on small, a bound on the external constant. So it's
Okay, let's thank Mark Gorghetto.